Hello, my name is Mikko Malinen, and this is a new version of uh, collected papers from last year, special issue on distance measures and machine learning. This article collection consists of 5 uh, short papers. We deal with distance measures and machine learning. And here you see the topics. We go through all of them in a quite quick uh, video and yeah uh, there's a preface that says, for example, that if you want to cite some of these papers, you can use this kind of reference. And here's papers are written in Times New Roman font, and those are the nodes of the graph here, and the connections between the papers are drawn as arcs between these nodes. We see that there are 3 papers on distance measures and 3 papers on machine learning, totally 5 papers. And first paper is about distance metrics, and very commonly used distance metric is Euclidean distance. Here we see that Euclidean distance is the let's say normal distance between 2 points in space. Here this here, and Manhattan distances, we take the distances along coordinate axis perpendicular to coordinate axis. Here we have 2 coordinates, and we add those distances along the coordinates. And infinity norm is the longest distance along coordinate. Here it is, this one here. And in this paper we use the Manhattan distance instead. We replace Euclidean distance with Manhattan distance and look how much that correlates. Those correlates each other, and how much it depends on dimensionality, for example. And to see the efficiency, we need to know how much different calculation operations take in time. In processor, there's clock cycles, and addition takes one clock cycle. But we assume that these what are written here is, for example, rising to power of 2 and taking absolute value and so on. How much those take in a processor, how much those take time in the processor. And these values are taken from 8051 microcontroller. It may be different for some other processor, but this was available. This data was available for me, and the Euclidean distance is a normal distance what is normally used. And here we see that calculating Euclidean distance takes 6 times about 6 times dimensionality 60, and Manhattan distance takes about 3 times this dimensionality. So it is 2 times faster. It's more than 2 times faster to calculate Manhattan distance instead of Euclidean distance. So there may be some applications where we need speed, and this can be used, but we need to look at also the accuracy. We used this kind of data sets where there are 2 Gaussian clusters and the overlap is different in different data sets. And also the dimensionality is different. We have all the combinations up to dimensionality of 1024. And here is the correlation with Euclidean distance as a function of dimensionality. Correlation between Euclidean distance and Manhattan distance. We see that it's near 1, and that as a dimensionality is here, and it starts from 2 and increases to 1024. And the lowest point is here with dimensionality 4, and it's something 0.97, 98 maybe there. So we can see that this correlation is very high. It's near 1. And this is the overlap is constant here. We see the next graph is we take the cluster overlap. This is just number here. This 100 is very much overlapping clusters, and 10 is not much overlapping. So here we see that also the correlation is very high. It's 0.996 or something at minimum, and almost 1 at maximum. Here we have also another graph. We have a scatter diagram for Euclidean and Manhattan distances. We have an x-axis, we have Euclidean distance, and y-axis Manhattan distance. And we see that the regression line, if we draw it here, it's almost linear. And why this is oval here, or ellipse, it's because of the datasets are, as we saw earlier, it's Gaussian clusters, and this, I think this is this must be one cluster here, and so on. So conclusions: Manhattan distance can be used as heuristic for Euclidean distance, and if we make further work, we can try clustering and see with this new heuristic and see how much results differ in comparison with using the Euclidean distance. And these datasets are from University of Eastern Finland Machine Learning Unit. There are many datasets, very useful in testing clustering algorithms. If it's good or comparing, for example, to clustering algorithms. Then the next article is complexity of infinity norm. This is the same figure as earlier, and the infinity norm is here, the longest coordinate. Longest coordinate distance along the longest coordinate, and it's the maximum of these distances, this and this. And there's an algorithm to calculate the infinity norm. We go through all the dimensions, take the absolute value of distance between 2 points along this dimension, and if this distance is bigger than the earlier found, then we assign this distance as the maximum distance. We go through all the dimensions, and at the end we output the maximum distance. Here's the clock, how many clock cycles this takes. This is a little bit mathematics but I go fast this, and you may check later. There's also reference here. The idea here is that there's also another reference. This is to my earlier paper, where if we try all the distances along the coordinate axis, the first try, first coordinate axis, we surely go to the if block in this algorithm. Next coordinate, the probability is half, 1/2, and third is 1/3, and so on. This is from my earlier result. Applied a little bit to this new situation. So this is the average numbers of visits to the if block. And it is here in the middle. And the mathematics book, calculus, says that there's bounds this here involving integral is smaller than the average number of visits to if block, and this here is bigger than the average number of visits to if block. So the average time complexity is dA. We see also here that this is the same expression is here, and then we can write the bounds, upper and lower bound, this line, and solve it in integrals. So there's also only a linear, only a logarithm added to this base complexity. So this is the result. This a little bit more complex than the Manhattan distance, but faster than Euclidean distance, we saw in the paper number 1. And here are the references which I pointed out earlier in this paper. This is my earlier paper, and this is the mathematics book. Let's see if you want to look at this a little bit more. This is available from my homepage. You can find it by searching my name from the internet. Okay, then determining number of clusters from pairwise distances. There are points in space. We can take pairwise distances Euclidean distances between the point pairs and make a histogram of those and make it so that there are 1000 pins in that histogram, and those pins will be the uh, input for a neural network. It is normalized so that the values are from 0 to 255. This from technical reasons. It doesn't actually matter if these are normalized or not, but here we have normalized those, and we have totally 18,020 data sets consisting of variable but highly overlapping Gaussian clusters. The number of points of those datasets are from 100 to 1000. Number of clusters is from 1 to 10, and dimensionality is from 2 to 3. And the sizes of individual clusters are random, so that the total number will be n, but this ni size of cluster is random. We divide those datasets into training sets, about 14,000 sets, and test sets to 3,600. And there are, as I said earlier, this input layer is 1,000, size of 1,000, and then it's followed by fully connected layers of 1,000, 1,800, 500, 300, 110, and then a softmax layer and classification layer. And let's look at this figure a little bit more. It's hard for human also to see here how many clusters there are. But there are 8 clusters here. There's one, there's other, and so on. But this computer can see with some accuracy. And here are the results. Percentage of times the number of clusters was determined correctly. This proposed method, this neural network method, came second almost the same as the best, and clearly better than the others here. And we can conclude that it works quite at the level of best classical methods. And further work later increased the diversity of datasets, so increasing the dimensions, for example. And if you're interested in these other methods, you can find from this book explanations for these other methods. Then, article number 4, NP-complete problem solving needs exponential amount of neurons. This is neural networks, and we may have heard NP-complex problems, we make an assumption that P is not equal to NP. This is one of the problems, biggest problems in mathematics and computer science. If P is not equal to NP, then NP-complex problems are exponential time. We use this here in this paper. And I'll go to this figure first. If you want to calculate the output of a neural network, we must go all the calculations along the forward direction. There are weighted summations. There are bias for each neuron, and then the activation function must be calculated. And if these layers are these neurons, how many S neurons are in this neural network, and there are maximum number of calculation operations when these neurons are put as equal sized layers in the intermediate, two intermediate layers of equal size. And if the equal size is not possible, there's one bigger is the other layer, then we put the nearest to the input layer. Then the number of calculations is biggest. And at least after some small amount of neurons, after which this arrangement makes the maximum number of calculations. And this idea is here that is the maximum number of calculations. How much does it take time to calculate through this network? It is calculated here, continues here, and we see that it takes polynomial time to calculate it through. And with this, if we use the just plain S, the number of neurons, then this is polynomial, and we cannot solve NP-complex problems. We must put the S exponential. Then this here comes exponential, and it is needed to solve NP-complex problems. There is the same with the unequal number of neurons in network in intermediate layers. It comes the same result. And we have shown that solving NP-complex problems by neural networks needs at least exponential amount of neurons. And then the last article, number 5. A bad start sometimes leads to a good end. That is how it is in random swap. This is a little bit entertaining because we have see that this is true only for one data set. We tried also with other, and it didn't go like that. But the idea is that if we start the random swap clustering algorithm running that, we take 3 runs, and in the first second, one is best in the first second, and it's the middle and the worst in the first second, and this order is maintained until some point, and there is no clear order, and then at the last at the end of the run, this is exponential this axis, so this is quite a long time here. So the order is reversed, so the best becomes worse and the worst becomes best. And here we have here we have 100 runs. And red lines are best in the beginning, worst in the beginning, and blue lines are best in the beginning. And we see that maybe it cannot be seen from here, that the order is reversed statistically, but we can magnify view, and we see that the red lines, the worst, it was worst, yes, it's worst, as it should be. The worst comes best in the end, here, and best in the beginning comes the blue curves comes worse. This is only for this dataset bridge, and here is also start MSA, the rank of that scatter diagram. This is scatter diagram, and this is rank of MSC in start and rank of MSC in end. And the linear regression is it shows that it says as negative dependency on MSC on start. This actually, there are some assumptions in the linear regression. Some statistics must be almost hold of the data points. It's perhaps not doesn't hold here, but we can see that if we calculate the regression line, it is decreasing. And this reference here, actually, this scatter diagram comes after the references. It is not normally the case, but I didn't notice this when I was writing this article, but this reference is here for the random step algorithm. If you are interested, it's very good algorithm for clustering. It finds the global optimum, minimum of MSC, or a good MSC if executed long enough. So here were the articles, and I repeat that if you want to see this paper as a PDF, you can go to my homepage, which you find from the internet by my name, writing my name to search engine, and that's it. So thank you for listening, and see you next time.